Okay, we are starting a big unit on something called enolates. And enolates come from carbonyls. So let's look at carbonyls. Let's look at a carbonyl. Let's look at acetone. What happens to acetone? Acetone, also known as 2-propanone or propane 2-one. Okay, so what happens to acetone? We've learned that really strong nucleophiles can attack a carbonyl. So this is one thing that happens to carbonyls. So carbonyls are weak electrophiles. Weak electrophiles. That's great. Well, it turns out the carbonyl, other things happen to the carbonyl besides simple attack by nucleophiles. And this is going to be chemistry that's going to occur at the alpha carbon. So here's the carbonyl, and next door we refer to that as the alpha position. As it turns out, if you have a strong base that reacts with your carbonyl, one thing that base can do is pluck off that hydrogen. Now the anion that I'm going to draw, the conjugate base, of this ketone, and since the ketone is giving up a proton, really it's behaving as an acid. Now just because something behaves as an acid doesn't mean it's HCl and super strong. It's a very weak acid. But we form this anion, this conjugate base. And this conjugate base looks bad to me because where's the anion? Well, it's on a carbon. And we know carbon's not very electronegative, therefore carbon is not very stable when it bears a negative charge. So we think this would be a really strong base. It's a pretty strong base, but it's not as strong as we would expect because of resonance that we can draw. We can delocalize that negative charge into the carbonyl. So having the carbonyl next door allows for resonance. So we have multiple resonance forms. And between these two resonance forms, 1 and 2, I would expect number 2 to be the better form, the better Lewis representation. Technically we might say it's the major contributor. And the other form that I drew is a minor contributor. So in fact, this hydrogen, alpha to our carbonyl, it has a pKa of about 20. Now that's not very acidic, don't get me wrong, but it's not as non-acidic as something like methane that has a pKa of 50. And for methane, we'd say, well, of course you can't deprotonate that hydrogen because you're going to make a carbanion. Well, here we have another molecule, this ketone, and when it gets deprotonated, it makes a carbanion, and yet the pKa is 10 to the 30th times more reactive. That's a number I can't even conceive of, 10 to the 30th. So this is actually surprised, this anion, and based on its different resonance forms, is actually pretty stable. This anion has a special name. It's called an enolate. And the fact that enolates are fairly easy anions to form if you use a strong enough base, so our base plays an important role here, then you can form these anions. And as it turns out, interestingly, even though this form number 1, is the minor contributor, when it comes to chemical reactivity, enolates tend to react as if they are carbanions. So they tend to act as if they are the carbanion resonance form, not the oxygen anion resonance form. So we're going to find these enolates are extremely useful, but we're going to have to pay attention to what base we use. And then, of course, what are we going to do with these anions? They're going to be nucleophiles, and we're going to react them with other electrophiles. But enolates are a really important reactive intermediate in organic chemistry.